All right. Thank you so much, Dr. Miller. It's been such a delight to be here today and be in a virtual room full of people who care about a lot of things I care about. So yeah, thanks so much for including me. I'm here to talk a little bit about a case of modern mathematical development and try to provide an understanding of it from a Thomistic Aristotelian background. So we'll start here with a reference that has been made. I lost count how many times today. Aquinas's definition of mathematics. Mathematics studies what exists in matter and motion, considered apart from matter and motion. The question about something like Dedekind's real numbers comes up because some of these math objects, like sets or figures in non-Euclidean geometries, don't seem to exist in matter and motion, or at least not in the same way that sort of extension and number do. Some of these modern math objects have properties that do not belong to quantity as we sense it, like the real numbers, or they seem to have a little relationship with quantity at all, like sets, I think, or categories. So in this paper, I use Dedekind's real numbers as a case study for applying the Thomistic Aristotelian framework to incremental historical developments in the subject matter of mathematics, especially after Descartes' innovations in his geometry, 1637. So my thesis here is that at each step of this historical progression of math objects or developments in math ideas, the properties of new theoretical mathematical objects reduce to some properties of the original mathematical objects that exist in matter and motion. So I'm introducing a little terminology here. It's pretty straightforward. I call original math objects the things like the natural numbers and extension in 3 dimensions. And I call theoretical math objects anything that's sort of like more developed or more recent, I guess, than that. I want to say something briefly about constructivism, because the term has come up a few times, and it's going to come up on the next slide. I want to say I think the term constructivism has come up in different senses so far today. There's one way in which we look at the construction of something like a circle, I think, without which you can't do very much geometry at all. As you know, that is a construction, right? Or maybe better yet, the equilateral triangle or something, right? That is a construction, but it's a construction that's so closely tied to those original math objects that I think we can include that kind of object in a very strictly realist philosophy of math. In contrast, there's a kind of constructivism that I think is opposed to mathematical realism. And certainly that's how the phrase is used in sort of current philosophy of math. So I'm making that distinction because it'll come up a little bit later when I'm talking about myself, but it's going to come up right now when I talk about Jean Rioux. So this is just for some framework context, what other Thomists, Aristotelians have said about the same sort of question I'm trying to grapple with, which is how do we account for these developed mathematical objects? So in Rieux's 2023 book, he defines the legitimate mathematical objects as the natural numbers, magnitude, and 3 dimensions. What I call original, he calls legitimate. What I call theoretical, he calls illegitimate. So you can see how our opinions differ a little bit there. These other mathematical objects, the illegitimate or theoretical, for Rieux, they're part of the art of mathematics, but not the science of mathematics. And they're purely a result of invention on the part of the mathematician. So he holds this, I think, strong realism about the original math objects, but it's combined with constructivism, I would say, in the strong sense about the theoretical math objects and seeing those as like opposed. A constructivist might say something like, there's no basis of mathematical thinking in material reality. It's purely the creation of a human mind, et cetera, and so on. All right, and then Timothy Kern's 22 paper, we have a sort of similar stance, although he takes a different, comes to a different conclusion for him. Modern math objects properly belong to natural science, but not to mathematics. And again, we have like a limited realism. He's a realist about the original objects or the quantity as such objects, but he's not a mathematical realist about derived quantity. The thing that stands out to me about both of these takes is that they're both ahistorical. Both of these authors sort of pick things up right in 2022 or 2023, and they try to say, okay, what kinds of math objects are available, and then sort them into these categories of legitimate or realist or etc. So what I'm proposing in this, one of the things I'm proposing in this paper is a historical approach. So I'll give you 3 reasons I think it's worthwhile to look at the history of the development of some of these math ideas. And then I'll talk about the plan for the rest of the talk. So one reason I think to take a historical approach is that math, I think more than any other subject we learn, is taught without any reference to history. And I mean, maybe you heard something about Pythagoras when you learned the Pythagorean theorem. But in general, I think due to philosophical movements in the 20th century, the way we learn math just has very little reference to its historical development. And I always think it's important to push back on that movement a little bit. So that's one reason, probably the least important. Another reason is to try to understand the motivations for the development of what I'm calling theoretical mathematical objects. I think it's easy for us philosophers to think about, again, we just sort of have this spread of math objects in front of us and we want to categorize them and think about them. It's easy for us to get caught in the mistake of thinking like, well, mathematicians just, they sit in their rooms and they come up with new things, and that sometimes is what happens. But in, I think, important cases, there's a strong motivation for creating a new way of thinking or a new way of working in mathematics. And so taking this historical approach, we can look at some of those forces and see, no, this really solved a problem, or this was really, a big step forward in the practice of mathematics. And then finally, the purpose of the talk, to illustrate the incremental development of these math objects and how they're still rooted, I think, in the original math objects. So to that end, I'll start by talking about Aristotle and Euclid. Just doing this historically. I'll give you some historical context for Dedekind's continuity in the rational numbers, which is where he develops the real numbers. I'll work through his construction of those real numbers, and then I'll try to sort of go back and provide an analysis of the real numbers, and then try to say some things more broadly as well. All right, so starting all the way back with Aristotle. Again, this is something that's come up many times today. I'm starting with the concept of continuity from the categories. Continuity is a characteristic of certain quantities by which the parts of a quantity share common boundaries. Another way of saying, I think, the same thing is that a single division of a continuous quantity divides it into 2 orderly parts that do not overlap with each other, or where one of them ends, the other one begins, and there's no gap. This distinction between continuous and discrete quantity, we have numbers, they are not continuous. We have magnitudes, and they are. Numbers have a notion of measure, magnitudes do not. I apologize, I know this is review, but it all comes up later. I take this distinction as an ontological fact. I know Daniel's paper earlier was sort of working on whether there is sort of a nature of quantity generally or a science of mathematics generally. But I'm taking this as just as given that there's nothing in the material world as we sense it that corresponds to numbered extension or continuous number. However, both kinds of quantity, the continuous and the discrete, admit of equality and of greater and less. I think it's important that understanding these as distinct aspects or distinct kinds of quantity, equality between 2 lines is not the same thing as equality between 2 numbers, right? There's an analogy between them because we can see that equality applies to both, but they're not equal in the same way. They're not greater in the same way. They're not less in the same way. All right. So I'm gonna do a little bit of history of math. Here, the next few slides. I apologize if it's all review, but I think it's all worth pointing out. So this is from Euclid's book 10, where he works on the incommensurables and the irrationals. He defines an irrational line as something incommensurable with another given line, or that there is no part of either line that completely measures the other. A third way of saying the same thing is that these lines do not have to one another the ratio that any number has to any other number. So we have here an example, the square on A with its diagonal B A and B are irrational. Well, they wouldn't be for Euclid, but we can take them that way. The point is, right, that you can divide A into 7 billion parts, and taking 1/7 billionth of A, it will not measure B equally. There will always be some excess or some defect. One of the reasons I point this out is that later we're going to want to define irrationals as numbers, right? And numbers have the notion of measure, and irrationals precisely don't have any notion of measure, or two lines that are irrational to each other can't measure each other at all. So a little bit more of that history. I think the first maybe theoretical mathematical object is Descartes' cipher in his geometry in 1637. He proposed this redefinition of the multiplication of lines that always produces another line. Before this, it wasn't impossible to apply algebra to geometrical problems, but your ability to do so is always limited by the fact that multiplying two lines together would give you an area, multiplying a line and an area would give you a three-dimensional object, and then multiplying lines by a three-dimensional object after that sort of ran out of meaning because you'd run out of dimensions. So Descartes comes along, he redefines this multiplication of lines. He can now use all of the methods of algebra to solve geometrical problems, and in fact, solved a 1,000-year-old geometrical problem, 5-line locus from Pappus, with just in 20 pages. It's really marvelous, very exciting. However, what he's done here is effectively, or at least in practice, to a certain extent, collapsed that distinction between the continuous and the discrete, right? In this case, he's made the continuous like the discrete in that multiplying two continuous things give you the same order of that continuous thing, just the way multiplying two numbers gets you another number. As a result, right, having sort of made only half this comparison between the continuous and discrete, when Leibniz develops the infinitesimal calculus, not much later, this question comes up. What about if some theorem of the infinitesimal calculus is true over the domain of continuous magnitude? How does it apply to number? Mathematicians just sort of started doing this and assuming that it was going to work, but without this rigorous basis. And then I want to say the third sort of thread that's motivating Dedekind, and we'll see a text from Dedekind in a second that lays this out, is that in the 19th century, there was a lot of pressure on mathematicians to try to establish rigorous philosophical, logical bases for all of the mathematical projects that they were engaging in. So again, I apologize if that was all review, but now we get to talk about Dedekind. So here's his motivation. The statement is so frequently made that the differential calculus deals with continuous magnitude. And yet, an explanation of this continuity is nowhere given. Even the most rigorous expositions of the differential calculus do not base their proofs upon continuity, but, with more or less consciousness of the fact, they either appeal to geometric notions, or those suggested by geometry, or depend upon theorems which are never established in a purely arithmetic manner. So this is the problem Dedekind wants to solve. All right, so we'll go pretty quickly through this. Just a brief summary of how Dedekind constructs the real numbers. He starts off this paper with a very brief, I think it's like 3 sentences, explanation of how you get the rational numbers from the natural numbers, coming up with 4 sets of numbers, each of which is built on the set before. It's obvious that any result of multiplication or addition on the natural numbers only gives you another natural number. You can subtract some natural numbers from others, but not all from all, or you can't divide all natural numbers by all numbers and still get a member of the natural numbers. So this progression of these 4 sets of numbers are all just an application of one of the 4 arithmetical operations. For subtraction, we get the integers and the wholes, including the negative numbers, and then the rationals as a result of permitting ourselves to divide all members of the whole numbers by all members of whole numbers. What's interesting about this, I think, and this will be similar to the construction of the real numbers, is that it's by operating on members of the previous set that you then have a member of the new set. So a rational number is the result of dividing 2 whole numbers by each other. You get a member of the rationals. All right, so here's the problem that he wants to solve. Rational numbers are not continuous. He makes a comparison to the continuity of a straight line to make this obvious to his reader. Just even from our diagram, figure 1, if we laid out line B, the diagonal of the square, on this number line, and let line A be the length 0 to 1, this length square root of 2 is certainly a point on that straight line. We can cut it off using Euclidean methods, but it's not included in the rational numbers, obviously. So as a result, and this is just a restatement of that fact that the rational numbers are not continuous, there's no single cut in the rationals that corresponds to the square root of 2 on the straight line. To produce this cut, oh, sorry, something happened to my Greek letters here. To produce the cut around the square root of 2, we would need both a rational number alpha that's infinitesimally close to the square root of 2 but less, and a rational number beta infinitesimally close to the square root of 2 but greater. And this is exactly, exactly fails that condition for continuity that we took from Aristotle. All right, so here's the goal. We want a continuous set of numbers, and it has to include all the irrationals, right? Because we've already seen how otherwise there will be these gaps. Again, I've lost only one of my Greek letters here. So this is the construction of the real number, the square root of d. Lambda is a member of the set of rationals. So d is constructed by being greater than lambda squared and less than lambda plus 1 all squared. And then we prove that the square root of d is irrational. If we suppose it's rational, it causes a contradiction. You can prove that a rational number y is both greater and less than the square root of d if you assume it's rational, so we know it has to be irrational. Dedekind first shows that the square root of d cuts the rationals into 2 orderly or non-overlapping groups, one set greater than the square root of d and one set less than the square root of d, and that this cut is produced only by the square root of d, right? Doesn't require 2 cuts or two values. Dedekind makes a grand gesture here. He says, let all such cuts in the rationals exist in the set of the real numbers. I've always found this move somewhat surprising. It's just pure fiat, right? He's just like, yeah, okay, now they are. Now I've made the real numbers. However, one of the reasons I took us through the process of creating the 4 original sets of numbers is to say that sort of has already happened, right? If you accept the construction of rational numbers based on whole numbers, you've kind of already said, well, by fiat, let all the rational numbers so defined exist, right? All the results of all 4 arithmetic operations on the natural numbers. Dedekind finally proves that each such cut in the rationals produced by a real number is created by one and only one member of the reals. And again, we have that building from the rationals to the reals. And then as a result, we have this conclusion: the real numbers are continuous. It's easy to imagine, and I've probably made this inclination stronger on the previous slide by showing sort of the number line, the comparison between the rationals and the continuity of a straight line. But the real numbers properly are just a set of numbers, right? It's not a number line, right? We can easily use them to create a number line by simply laying the reals onto a straight line. But I think the best expression of the real numbers would just be like any set of numbers, sort of a list with ... at either end, as we were just hearing about in the previous talk. All right, so that's our construction of the real numbers. Next, I'm going to talk a little bit about abstraction in Aquinas. So this is going back to that same commentary on Dedekind. The punchline here is, I want to say the development of the real numbers is not happening by abstraction, or at least not by abstraction in the sense we mean it when we're talking about the definition of mathematical science or natural science or metaphysics. In this commentary on the Dedekind, we get this fact that abstraction is the act of thinking of one thing without another, when the 2 are together in reality. As a result, right, there's sort of, we can say abstraction generally, and it means all 3, but really, strictly speaking, the basis of metaphysics is separation of principles, not abstraction. And that only two types of abstraction are possible, either of a whole from its part or of form from matter, which are obviously associated with natural science and mathematics. So I want to say here, again, as I've already, I jumped ahead to say, what we've just gone through with the real numbers is not an example of abstraction, but instead, Dedekind's construction combines some aspects of the continuous with some aspects of the discrete, leaving others behind or prescinding from others. And there's no underlying subject that's common to both continuous and discrete quantity, right? So there's no abstraction, because abstraction is the act of thinking of one thing without another when the two are together in reality. So even though even though both continuous and discrete quantity are a kind of abstraction from sensible matter that then exists in intelligible matter, they abstract different aspects of that matter. In one case, the divisibility of one substance, like parts of one substance from itself, and in another case, the divisibility of different substances from each other, getting you first continuous and then discrete quantity. All right. So here's what I want to propose. The best way to understand the kind of existence that Dedekind's real numbers have. So I want to say Dedekind's real numbers have relations among themselves that are like the relations among Aristotle's continuous quantities, right? Based on this analogy between equality and greater and less in continuous and in discrete quantities, right? One of the reasons we went through the origins of our thinking about historical thinking about irrational numbers is to point out this is just an analogy, right? The primary characteristic of number, or one of the primary characteristics, which is that it is a measure, is something we completely leave behind once we've included irrational numbers into our definition of a set of numbers. So here we have something like it's number like in one sense, but it's really more like continuous quantity. So I want to say the relation between two real numbers is like the relation between points on a line or the relation between two continuous quantities, but we've added something number-like to it. The real numbers, if we put them in at something like a number line, they do provide us a measured means to compare points on that line, which is something more than we have if we're only comparing points on the line or the lengths of two quantities with each other. All right. Further, I want to say these relations, which are sort of the way we can compare the real numbers to different aspects of the continuous and discrete, and this is something I said, I think, on the previous slide as well. It's not abstracted from any quantity generally. It comes with this precision or leaving different aspects behind. So our concept of the real numbers cuts off some aspects of the proper forms of number and magnitude, and then unifies the remaining properties through a construction. So the construction of the reals, I want to say, is completely determined by other properties of number and magnitude, specifically the property of number by which numbers have the notion of measure, although not perfectly, right, because we've included the irrational numbers, and the property of magnitude by which it is continuous and admits of greater and less, the way something continuous admits of greater and less. So here's where this question about, I think, constructivism comes up. I hope it's clear from the way I've laid this out that this kind of construction is different than, say, the construction of the equilateral triangle in Euclid Book 1, Prop 1, because we've made not just an object out of sort of we've made not just a figure out of sort of the accepted basic mathematical objects of extension and number, but some new kind of object itself, right? Some kind of new substrate that could then be formed into a new construction, like a number line or like a set, right? A set is an interesting example of a construction. All right, I'm already at my conclusion. I do have more to say though. So here, I think we can come all the way back to that first slide and say something that's always stood out to me. I know I'm not the only one. I think I probably first read this in James Franklin paper many years ago, that Aquinas does not define mathematics as the science of quantity. And that by defining mathematics as a science of what exists in matter and motion, considered without matter and motion, he leaves an open door for including things in the science of mathematics, in the subject matter of mathematics, that are not just the immediate things that we abstract as formed from matter in that, definition of mathematics that we get in the commentary on the De Trinitate. And I want to say the real numbers are an example of this kind of theoretical mathematical object that's rooted in what exists in matter and motion, even though, is not abstracted directly from anything that exists in matter and motion. The real numbers are based in these characteristics of the original mathematical objects, as I've said, even though we don't find their equivalent in the material world. And then here's, I think, where I'm probably making my boldest claim. The real numbers, I think, by being completely determined by these properties of what exists in matter and motion, therefore fit this definition of the subject matter of mathematics. So further thoughts here, I want to go back to that realism and constructivism point. I want to say that by relating theoretical math objects back to original math objects, and as I've said, I've just wanted this paper to be a case study to say, here's what that might look like. And you could apply it to, certainly to Descartes' ciphers, as I've indicated here, but to set and category and, the imaginary numbers, right, complex number, all these other sort of instances where even as a new math object is being invented, it's in reference to and sort of in conversation with the kinds of objects that have come before it, and usually, invented or constructed, however you want to think about that activity, in response to a mathematical problem that the mathematician wants to solve. And that I want to say this kind of constructivism is again more. There's more construction happening here than just constructing a equilateral triangle, but less than someone who would say, like, these theoretical math objects are the result of pure human invention and have no reference back to material reality. Similarly, I'm interested in questions in applicability of math in general. Andrew Mellick actually yesterday was just pointing out to me, people often refer to this one Wigner essay, the unreasonable effectiveness of mathematics in the natural sciences, interpreting it, as really only saying what its title says, right? That it is unreasonable that mathematics is effective in the natural sciences. But instead, what he's really doing in the paper is pointing out that it's surprising that objects like, Hilbert spaces, like very, very developed and very, we might say in a non-technical way, abstract math objects, still find a use in the natural sciences, and that fact is very surprising. And I see I see what motivates that, right? I think what I'm suggesting here, if it works, is one way to try to answer that question and say, well, the reason Hilbert spaces have some applicability in the natural sciences is because they have some relationship back to the original mathematical objects. In the case of something like Hilbert spaces, and in many inventions, or maybe inventions is not the word I want to use, developments in modern mathematics, it is difficult to trace that line directly, as I think I've been able to do with the real numbers. On the other hand, just the fact of consistency in a lot of mathematical theories, I think, is very often the way we prove consistency in a new mathematical theory is by modeling a previous mathematical theory we already know to be consistent. So even if all we can say about a whole new mathematical theory is that it's consistent by using a model like that, that's still a reference back to the original math objects and what we first abstract from matter and motion. I will very briefly say that I mentioned briefly this question about math teaching being ahistorical. I think further, the way that we present math as just sort of like existing all at once and having no progression to it is one of the reasons that a lot of people really struggle with math. And especially when it comes to this collapse of the distinction between continuous and discrete quantity, because the world as we sense it doesn't have anything like a number line in it. And because you probably met the number line, we probably all met the number line, sorry, in second grade or soon after. I think math, especially for young students, very quickly becomes detached from material reality. And that looking at historical progressions like this not only helps us answer sort of these bigger questions about the ontological status of math objects, but can also indicate for us ways that we can improve the way we teach math. All right, that's my talk. Thanks so much.
All right, thanks, Maureen. Thanks for staying close to time. So now we have plenty of time for questions. Yes, Eduardo.
Yes, thank you very much, Maureen, and thank you for clarifying that. Yeah, absolutely. St. Thomas never talks about math as the science of quantity. In fact, the first one who comes up with that definition is Johannes Müller von Königsberg, also known as Regiomontanus. Before him, nobody says that, so St. Thomas doesn't say that, and Aristotle doesn't say that. So, thanks
Right.
for setting the record straight. There is one thing that I'm really interested in, whether one understands construction in a constructivist way or not a constructivist way. There's still some kind of construction, right? And
Yes.
in art, the subject is what is produced. In the case of science, the subject is what is contemplated only because of necessity. It cannot be otherwise, therefore we just contemplate it. But I'm really interested here in the use of number because, as Aristotle says, St. Thomas also explains, the definition of a thing is taken from its principles. So what would be this definition of number, which seems to be very general because it would include like discrete quantities and irrational numbers and all these things.
Yes, that's a good question. I don't know. That's a really good question. I'm not sure how you would put it into a sentence. I think whatever I've indicated about like the work that Dedekind does as he's defining the real numbers would have to be included in that definition somehow. That it is a set of numbers based on a certain kind of relationship between the rational numbers, that each member of the set cuts the set into two sets, one greater, one less, one and only one cut, that kind of thing. Like, I think all of those things are part of what it means to be a real number. And that it's clear in Dedekind, and definitely wasn't clear in my presentation, but that the rational numbers also fit that definition, and so do the natural numbers, right? The natural numbers produce the exact same kind of cut in the set of reals as an irrational number produces in the set of the reals. So the definition of the set of real numbers, I think, has to be relating to that cutability, that perfect density.
Thanks. I was looking for the definition because once we know the definition, we can know what the principles are. So that's right.
Right. Yeah. Yes. Thank you.
All right, Daniel.
Yeah, Maureen, thank you for the talk. It's great. I was the point about the number line, I think, is a very good one in how it's presented in schools. Being a teacher, I definitely find that that's the case. That oftentimes it's not presented well. I had a question about it's maybe more to do with Dedekind's cuts, but the analogy, it seems that he's using the analogy of the number line, right, to talk about the different kinds of numbers. And even just the way that you would position square root of 2 on a number line, it would be through a sort of geometrical construction that would, like the way that we can even know the length square root of 2 would be by, constructing a square of length, side length 1, 1. So that seems almost like a categorically different type of mathematical object than a number or than a natural number, whole number, integer, or rational number. It seems to be more of like a geometrical kind of number, and almost a geometrical object. And so I'm wondering, I guess, what is the difference between irrational numbers as numbers and irrational numbers as more just a representation of the length of a line, of a geometrical line, because we can have, we can label lengths as Descartes did on geometrical figures with numbers, and then we can do that with the irrational numbers. So I guess I'm wondering if there is a distinction. Is there a distinction, and if so, what that is? That would be between the geometrical nature of square root of 2 and square root of 2 as actually an actual number.
Yeah, excellent. So to Dedekind's credit, and not to mine in this presentation, he makes it very clear when he has left the comparison to the straight line behind. So he uses a comparison to the straight line to indicate that the rationals have gaps. And then he says, okay, now we need to create a set of numbers that is continuous. And then once he's done that, we can then apply the real numbers to the number line again. But as he's creating the reals, he does it by this, by the cuttability of the set into two perfectly greater and less and non-overlapping parts. So like I'm gesturing as if that's spatial, but it isn't, right? Like in the nature of the real numbers, yes, each number itself is such a cut in the rationals. It's interesting. I mean, he famously uses the word cut, right? Dedekind cut, the Schnitt, which certainly seems to imply a strong comparison to something cuttable, which like has extension. But I think in a more proper way, we should think of that as some sort of division, or some sort of like ability to have parts that are greater and less numerically and not extension wise.
I guess even there though, even there, if you were
it's
to
really
say how
difficult
far
to
away,
talk about it, right?
how far away is that rational number from the irrational? What's the distance of that? It's an infinitesimally, close to it. How, like, I guess it's infinitesimal, so you can't say how big it is, but you could never identify the distance of any rational number from the irrational using a rational. You'd have to use an irrational,
right,
or length.
I think it's an instance where the fact that our mathematical intuitions come from material reality is going to get in the way of a purely theoretical understanding of the real numbers. Like I said, they are cuts in the rationals. That is that's how we understand them. But because of our association of cutting things and certain kinds of greater and less, and certainly the greater and less of continuity, with things that have extension, I think we almost immediately have an image of extension that applies to the real numbers. And this is exactly why the fact that they're introduced to us at very young ages and in ways that are not necessarily well defined can introduce a lot of confusion for people just learning mathematics. So I don't know if that satisfies the answer to the question. It's more just that theoretical, like in a purely theoretical way, there is nothing line-like about the real numbers, even though we in the construction needed to compare the continuity or lack of continuity of the rationals to the continuity of the straight line.
All right, Father Christopher, if you could just keep it somewhat short.
Yes, so my question has to do with the constructability of the reals, in the sense that in order to do the Dedekind cuts procedure, you have to do an infinite number of procedures, an infinite number of steps to cut and separate the rationals on the one side from the rationals on the other side of your irrational number. And so I don't think Aquinas would be happy with this, because he says you cannot do an infinite task or an infinite number of things, nor can there be an infinite multitude of things. So I'm not quite sure if Aquinas would be open to irrational numbers, because they are in a certain sense infinite.
You mean in more than the sense that the natural numbers are infinite?
Yes. So like there's no finite decimal expansion, for example, right? You have to have an infinite ongoing forever, non-repeating decimal expansion for an irrational number. And without that, you don't have one.
Right. That's true, but I mean, I think my concept of like square root of 2, I can express the square root of 2 as the square root of 2. I can express pi using the Greek symbol. And what I'm really expressing there in both cases is like a ratio that I've numberified.
But that's the point. You don't actually have the ratio. If you did, it would be a rational number.
Yes, sorry, a ratio of continuous magnitudes that I've numberified.
I'm not quite sure what that means.
Sorry, the side of the square to the diagonal. The ratio between the side of the square to the diagonal is what I've expressed, but that's no problem. Number-wise, like, as
these
square root of 2.
Things aren't commensurate, which precisely means there is no ratio.
Well, all
so
straight
when you
lines
say, when Dedekind says like, well,
other.
Just let there be a set of these things, right? It requires an infinite number of processes to get that. Whereas for an actual rational ratio, you might say you only need a finite number of steps in order to specify it.
To specify it, to count it, right?
Yep.
But all lines have ratios to each other, right? They might not have the ratio that a number has to another number. In the case of irrational lines, they don't have a ratio that another number has to another number, but they have a ratio. There's a ratio between, well, there's certainly a ratio between the diagonal of a square and its side. It's just not a rational ratio, right? So, and I admit, right, like I'm interested in trying to include something like the real numbers in a development of Aquinas's original mathematical objects. But like I've said, especially in talking about constructivism, I recognize that there's a difference between this kind of math object and the original ones. I'm not sure I agree with your intuition. I thought you were going to go a different way with this. I thought you were going to say that the real problem here is like Cantorian, orders of infinity, and we don't really get those until we have the real numbers, and so the real numbers are the real problem, and we don't have, if we didn't have them, we wouldn't have to worry about Cantor, right? Because that the orders of infinity come about because of the density of the real numbers, not because of their extension, right? Countable, the natural numbers are already countably infinite. Sorry, I'm saying all of these things out of order. But I don't think that the issue you've raised, if we can accept that it's acceptable to call something a number that has this very sort of loose relationship back to the natural numbers. Well, I don't want to use the word loose, that it has this very extended relationship back to the natural numbers. If we accept that, then I think we can use square root of 2 and pi and e in these numbers as numbers. But yeah, we can disagree about that as well.